I've always felt it's best to define the data model of any application before designing the code. After all, much of what the code will be doing is manipulating data, so how can you design it if you don't know what the data will look like? As mentioned earlier in this course, our example will have one transaction per record. On other blockchains, such as cryptocurrencies, it's common to have many transactions in each block. But on Salesforce, this would make little sense. By having one transaction on each record, all of the capabilities of Salesforce can be used with those transactions, from using declarative features to create blocks, to creating reports based on the ledger, to using search to search for transaction data. For our example, each block and its transaction will be stored in a custom object called ledger entry, with the API name ledger entry __c. The name field is defined as an auto number field. Now let's look at the other fields. We'll start with the transaction data fields and follow with the blockchain fields. This example will implement the Global Mantix Deal Ledger. Each transaction will contain the name of the opportunity and its amount. The opportunity name field is defined as 120 characters long, which corresponds to the length of the opportunity object's name field. The amount field is a currency field. These fields are not required. While logically you would want them to be required, making a field required has security implications. You lose the ability to use security configuration to restrict access and visibility on required fields. And we're definitely going to want the ability to limit visibility on those fields. There's no particular reason why a field can't be null from the general perspective of a blockchain, so we won't want to require the fields in Apex either. Instead, we'll prevent null values as needed using two validation rules, on the opportunity amount and one on the opportunity name, both of which result in an error if the field is blank. Generally speaking, you should only include static primitive fields in a transaction. You should not include lookup fields because they are represented by an ID value. Using a lookup puts the entire chain at risk if the referenced object is deleted. It makes it impossible to import a ledger from one org to another, as the ID value has no meaning outside of Salesforce, meaning that anyone auditing a transaction would still need access to Salesforce to understand the transaction. You should also avoid formula fields, as there is too much risk that their values can change, and any change would invalidate the entire blockchain. Not only that, but most formulas are not yet calculated during a before insert trigger, so in the implementation you see here, they won't work at all. Next comes a field called Transaction Field List. This will be a list of the API names of each field used to create the transaction hash. Now you may wonder, why we'd need to store this value? Wouldn't it always be the same? In truth, if the fields used in the transaction were always the same, you wouldn't need this field. Your Apex code could simply use a fixed list of fields. But what happens if at some point you want to add a new field to your ledger? Remember, the blockchain is immutable, so if you try to validate any of the older transactions using the new field, the validation would fail. So you need a way to keep track of which fields are used to validate each record. You'll want that field to itself be secured by the blockchain, so it also can't be tampered with. The field can be included as part of the transaction data. That way you won't need to publish the list of fields with that part of the blockchain that you are making public. This will be a long text field, and the length really depends on the maximum number of fields you think you'll need in the ledger. Don't worry, you can increase the length of this field later without invalidating the ledger. Storing the field list also makes it possible to define fields on the ledger entry record that are not secured by the blockchain, for example, lookup fields or formula fields. The final field included in the transaction is the transaction date field. The reason for including this in the transaction is to help add variation to the transaction hash values in the event that multiple transactions have otherwise identical data. If you just used the opportunity name and amount, someone could try a brute force attack, trying every possible company name and amount to come up with a matching hash value. Hard, but not impossible. The more fields you have, the harder such an attack becomes. Adding the date makes it much harder. You could even add a long random number to the transaction to make such an attack virtually impossible, but we're not going to go that far in this example. Next, we need a field to hold the hash of the transaction data. We'll call that field transaction hash. This field and all of the other hash fields will be 70 characters long, which is overkill, as the SHA-256 hash algorithm used takes up 32 bytes, which should be represented in 43 base 64 characters when using the kind of encoding called base 64. We add some characters to be safe and to allow for the possibility that Salesforce might need extra characters when storing the base 64 string. This field is not unique, as we don't really care if two transactions are identical and have the same hash value. Next comes the sequence number. Every block in the blockchain has a sequence number, with blocks numbered from 0. The sequence number is configured as a unique external ID field. This adds an index to the field, which improves performance when validating the entire chain. As to do so, it is necessary to iterate over all the ledger entry records in sequence order. The sequence number is included in the block hash. This ensures that it too can't be tampered with. The next field is the prior block hash, the hash value of the previous block. Like the transaction hash, it is defined with a length of 70 characters. However, it is unique and case sensitive. This field can be used to quickly query for the previous block. It will be null for the first block in the chain. Finally, you have the block hash, which we'll name block hash. This field will contain the hash of the block. Like the transaction hash, it is defined with a length of 70 characters. It is unique and case sensitive. It is also defined as an external ID to make it easy to query for a record based on its block hash. The hash is derived by applying the hash function to the prior hash field, the sequence field, and the transaction hash field. Now that we have the data and architecture defined, it's time to start writing some code.